Chapter 3 is on orthogonality. Maybe I should use the black marker. Chapter 3 is on orthogonality. So in chapter 2, we found the basis of the four fundamental spaces, and the easiest way to find components of a vector is when the bases are orthogonal. So that is why your coordinate axis in three-dimensional space, the I, J, and K unit vectors, they are orthogonal because it's much easier to find the components of the vector in each of these directions. So in this chapter, we are actually going to orthogonalize vectors, and then we are also orthogonalize vectors that are independent. And then we are also going to see that the two fundamental spaces in Rn and two fundamental spaces in Rm, they're both at 90 degrees to each other. They are also called the orthogonal complement. So instead of saying Ax is equal to B has a solution when B lies in the column space, we can also say it another way, that there is a vector Y which is in the left null space, where the left null space and the column space are orthogonal complements of each other. Then we can say if B will have a solution if B and Y are orthogonal, or if the dot product of these two vectors is 0. So orthogonality is just a continuation of chapter 2, where we just orthogonalize the independent vectors. So let's start with orthogonal vectors and subspaces. So orthogonal vectors and subspaces. A basis is a set of independent vectors. We know that a basis is a set of independent vectors that span a space, geometrically it is a set of coordinate axes. It is a set of coordinate axes. In choosing a basis, we tend to choose an orthogonal basis. If we cannot, then we can always orthogonalize them, an orthogonal basis. So basis converts the geometrical problem. Basis converts geometric constructions into algebraic calculations. Which simply means an orthogonal basis makes calculation simpler. For an orthonormal basis, so orthonormal is different from orthogonal. For an orthonormal basis can normalize the length of vectors in the basis to 1, and I'll tell you how to do that. So just an aside, if this is x and y, it's a two-dimensional picture, and you have this vector here, you have this vector here, so this is the vector x, and this point is 1, 0. This is x, this is y. This point is 0, 2. Obviously, this point is 1, 2. So we know from Pythagoras theorem that the length, so this is called the norm, is the length of x, and I'll define it in a little while. This is simply 1 square plus 2 square under root, which is equal to under root 5. So you normalize by this length, and the vector is going to have a unit, will have a length of unity. Okay, so length of x is this one. This is the length of x. This is also called the norm, the Euclidean norm. This is the norm of x. So this is the norm of x, and I'll define it in a little while. We can also test. For orthogonal. So test for orthogonal. So this is this inverted. It's not an inverted pi. This is a straight line and with on a base. This is symbol for orthogonal. So test for orthogonal vectors. If you have two lines here, then it becomes an independent symbol. So test for orthogonal vectors x and y is x transpose. This is from your basic physics, high school physics. This is equal to 0. The dot product is 0. It's a scalar. And then we also want to see how do we construct orthogonal x and y from independent vectors. So this is the Gram-Schmidt procedure, which is probably the last topic in this chapter, and we'll see how do we do that. So since vectors are orthogonal, subspaces can also be orthogonal. So subspaces can also be orthogonal. So we'll see probably in the next lecture, or maybe by the end of this lecture, fundamental subspaces meet at right angles, meet at 90 degrees, and subspaces are orthogonal in pairs. Meaning implies 2 in Rn and 2 in Rm. And hopefully we know what are the two subspaces in Rn. The two subspaces in Rn are the null space of A and the row space of A. And the two in Rm are the column space of A and the left null space of A. So we'll have an alternative definition for the solution of Ax is equal to B once we show that these two subspaces are orthogonal to each other. Okay. So what are orthogonal vectors? Before I define the norm, let me give you a definition and then we'll prove this one. In Rn, x square, where x, let me define this first. In Rn, where x is x1, x2, because it's Rn, so it's just x components, is xn, then I define the length squared as x1 squared plus x2 squared. Assume these are all real. Assume these are all real numbers. So real numbers. So x1 square plus x2 square plus x square n, and x is simply the positive square root. The positive square root is the positive square root is a positive square root is a positive square root of x square, and this is also equal to, if you still recall the dot product, this is simply x transpose into x, or positive square root of x, and this is also equal to x transpose x, positive here. Okay, so let's define orthogonal vectors. How do we define orthogonal vectors? Orthogonal vectors. So what is the test for orthogonality? We know from high school physics that the dot product should be, the angle between the two vectors should be 0. So let's prove this one. So the test for orthogonality, it's just a repetition, but just to reiterate, how do you figure out that the vectors are orthogonal? So test for orthogonality. The test for orthogonality is like this. So we have this head to tail rule. So this is some vector y. This is right angles, some vector x, and this one by head to tail rule is x minus y, right? So x minus y, x minus y plus y would give me x. So this is the head to tail rule. So by Pythagoras theorem, and let me write here, this x is actually x1 to xn. This y here is y1 to yn. And this x minus y is x1 minus y1. Each component is subtracted from the other, y minus yn. Okay. So by Pythagoras theorem, x minus y magnitude square, the norm square should be equal. This is not the magnitude, this is the length, but you don't say the magnitude of vector, you say the length of the vector is x square plus y square. So let's concentrate on this one, expand this one. So this is simply equal to, or the norm square. So this is x minus y1, xn minus yn, this vector, and the norm squared of this vector. The norm squared of this vector by this definition is simply the square of each of the components. So sum of the square of the components. So this would be x1 minus y1 squared plus x2 minus y2 squared plus xn minus yn squared. So if I expand this one, a minus b whole square is a square plus b square minus 2ab. This will be x1 squared from here, x2 squared from here, plus xn squared from here. Then we have y1 squared, y2 squared, and we have yn squared. So y squared, and then the cross product, which is minus 2 x1 y1, x2 y2 plus xn yn. Now this is equal to, by Pythagoras theorem, this is equal to this square plus this square, which is simply equal to this norm squared. This is y norm squared. So obviously, so this means, so this implies this cross product should be 0. So this implies x1 y1 plus x2 y2 plus x and yn has to be equal to 0. But what is this one? This is simply x transpose into y equals 0. So this is the inner product. This is the dot or the inner product or the scalar product, inner or scalar product of and y. Okay. I can also write this one as x dot y. I can also write this one as x comma y. So there are different notations. So I think your book uses all of these from time to time. Also, x transpose y is greater than 0. This implies the angle between x and y is less than 90 degrees, because you know that there is a cosine of theta involved here, and we'll probably do it in the next lecture. The angle between x and y is less than 90 degrees, is less than 90 degrees. And similarly, if x transpose y is less than 0, this is negative. This implies angle between, so this is the symbol for angle, I hope you know that, angle between x and y is greater than 90 degrees, and in the worst case, when it's 180, this is -1. Okay, so only vector that is orthogonal to itself is orthogonal to itself is the zero vector. Is the zero vector. Why? Because 0 is orthogonal to every vector in Rn. So if you take the dot product, obviously the magnitude is 0, so everything is 0. Okay, so if you have independent vectors, we can orthogonalize them using the Gram-Schmidt. What happens if you have orthogonal vectors? Are they independent? So if non-zero vectors are mutually orthogonal, that is every vector is orthogonal to every other vector, then these vectors are independent. And how do we show that are independent? So orthogonal vectors are independent, and independent vectors can be orthogonalized. So where's the proof here? So the proof is, so use the definition of independence. So let C1 V1 plus C2 V2 plus CK Vk equals 0. So this is so this is how you start proving independence. When you show that the only solution for this equation is the trivial solution, then you say the set of these vectors, these k vectors, are linearly independent. So let's do V1 transpose. So T is for transpose. Whether you write a capital T or a small t doesn't make a difference, as long as you know what this T means. V1 transpose into this sum, C1 plus C2 plus V2 plus CK Vk equals V1 transpose into 0, which is equal to 0. So it's a scalar now. And this implies, C1 into V1 norm square is equal to 0. Why? Because Vi dot Vj equals 0 when I equals j, I not equals j, and 1 when I equals equals Vi norm square when I is equal to J. So because these vectors are mutually orthogonal vectors, mutually orthogonal vectors. So since V1 magnitude, V1 norm square is not equal to 0, this implies C1 is equal to 0. And we can show this, this is true for all other CI. So also true for other CIs, which implies the only combination of V's of V's of V's of V's producing a zero vector is the trivial solution, which implies this set of vectors Vi 1 to k is linearly independent. Okay. So coordinate axis or vectors E1 to En, which are the columns of the identity matrix in Rn. These are the columns of In, columns of the identity matrix. So coordinate vectors E1 to En form simplest basis, and this is what we saw in the last lecture on in chapter 2, which was on linear transformation, that these are the standard bases. Form simplest basis in Rn, and our unit vectors with norm 1, with EI equals 1. Also, if x's are rotated, we have a new orthonormal basis. We have a new orthonormal basis, and this orthonormal basis is V1 equals cosine theta sine theta, and V2 equals minus sine theta cosine theta. This we also found in the last lecture. So let's digress for a moment and define what is norm. So what is norm? So a norm on a vector space, V is a mapping, is a scalar actually, is a mapping that associates with each vector V a real number, this one called norm of V, such that following properties are satisfied for all vectors u and V and scalars C and scalar C. There are not too many. And scalar C. And what are those properties? So there are three. So the first one is the norm of the vector is greater equal to 0 and norm is equal to 0 if and only if the vector is the origin. Second property, so this is always, the norm is always a positive number. So if you have multiplied the vector by a scalar C, then the norm is simply the magnitude of C times the norm of V. This has to be the magnitude of C. Why? Because this is a positive number. The norm is positive. You cannot just have C over here. And finally, U plus V norm is less than equal to the U norm plus the V norm, and this is the triangular inequality. So a vector space with a norm is called a normed linear space, is called a normed linear space. So what about the sum norm? So so we'll define three norms, and the one that we're going to use frequently is the last one, the Euclidean norm. So the sum norm is defined. So the sum norm is simply the sum of absolute values of its components. So maybe I write it over here. This is the sum of absolute values. The absolute values are also used because this may be complex too. The components may be complex. So sum of complex numbers. So sum of absolute values of its components. So sum of absolute values of its components. So Vs is simply V1 plus, it's the first component, the second component, and the nth component. This is also known as one norm, also known as one norm, and we'll see why. The second norm is the maximum norm. So maximum norm, this is also called the infinity norm, and again we'll see why it's called the infinity norm. So maximum norm by definition is, this is the definition. So whenever I put a triangle on the equal to sign, this is the definition. So Vn by definition is the maximum value of the absolute values, is V1 maximum Vn. So this is the largest number amongst absolute value, amongst absolute value of its components, and this is also known as the infinity norm. This is also known as the infinity norm, infinity or uniform norm, and you'll see right now why it's called the infinity or the uniform norm. So in general, we normed P is actually V1P plus V2P plus VnP whole raised to the power 1 over P for real P p greater equal to 1. So if p is equal to 1, this implies v1 one norm is simply vs. If p is equal to 2, this implies v2 equals v1 square plus v1 square plus v2 square plus, this is the component square, plus vn square, and this is the 2 norm. This is the 2 norm, or this is the definition of the Euclidean norm. This is the Euclidean norm. And for large p, the p norm approaches the maximum norm. That's why this is called the infinity norm. And with each norm, there is a distance function associated. So distance functions. For any norm, we can define, for any norm, we can define a distance function with the following properties. A distance function duv, which is u minus v, with the following properties, with the following 3 properties, And what are those 3 properties? The 3 properties are duv is greater or equal to 0, and what did I write here? And duv equals 0 if and only if u equals v. duv is a symmetrical function. duv, obviously is a scalar, is equal to the distance between u and v is the same as the distance between v and u, and where u, v belong to some w or some v or w vector space, and this is triangular inequality, duw is less than equal from here to here. So if this is u, this is w, this is v. So obviously the distance between u and w is going to be less than the distance between from here to here to here, is less than duv plus, unless they are in the same straight line, plus dv w. This is a triangular inequality. So if you want, I can do a simple example. You have u 3 minus 2, v equals minus 1, 1, minus 1, 1. This implies u minus v is 3 minus 1, which is 4, minus 2 minus 1 is minus 3. Okay, so this implies the Euclidean distance between u and v. Maybe I write it like this. So this is the Euclidean distance between u and v is simply the Euclidean norm between u and v, which is 4 square plus minus 3 square square root. So this is 25 square, which is 5. the positive square root. The sum norm, the sum distance due to the sum norm is again u minus v sum, and this is 4 plus absolute value of 4 plus absolute value of 3, which is equal to 4 plus 3, which is equal to 7. And the maximum norm, or the distance on using the maximum norm, is u minus v maximum is maximum of absolute value of 4 and absolute value of 3, which is equal to 4. So this is how you define distance functions for different norms. Okay, so let me define an orthogonal subspace, and before I end today's lecture, and then we'll start with the fundamental theorem of linear algebra. So let's define what is an orthogonal. So given this background, what are orthogonal subspaces? So orthogonal subspaces. So if two subspaces are orthogonal, then every vector in one subspace must be orthogonal to every vector in the other subspace. So if we say that the column space and the left null space are orthogonal, then this means that every vector in the column space has to be orthogonal to every vector in the left null space. Okay, so subspaces of R3 can have dimension 0, which is the origin, 1 line, 2 plane, or 3, which is the entire space. So this is okay, so this implies can be represented by lines, planes through origin, and in extreme case through origin, and in extreme case by the entire space, and in extreme case by the entire extreme case by only the origin, or entire space. So entire space dimension is 3, origin dimension is 0. This is a line and this is a plane. Okay. So subspace 0, subspace origin is orthogonal to all subspaces. A line can be orthogonal to a line. So a line can be orthogonal to a line. A line can be orthogonal to a plane, which means if this is a plane, the tablet I'm writing on is a plane, then the line sticking out of the tablet or lines going through the tablet is also orthogonal. So line can be orthogonal. Line can be orthogonal to another line or plane. However, what about if you have two planes? And we know from chapter 1 and probably the first lecture, when you have two planes, they intersect, and the intersection is a line which is common to both. So however, a plane cannot be orthogonal to another plane to another plane, y to another plane, because the line of intersection is common to both, is common to both planes. So obviously this vector, since it's not zero, it's not going to be uh, orthogonal. So the two planes, when they intersect, they are not orthogonal. Two subspaces. So two subspaces V and W of same space Rn are orthogonal if every vector V belonging to W is orthogonal to every W belonging to W such that V dot W is equal to 0 for all V and W. So that's the orthogonality condition. So let's look at this example before we close today's lecture. V is spanned by, so this is the basis for V. V is spanned by these two vectors, 1, 1, 0, 0 and 1, 0, 0, 0. 1, 0, 0, 0. Okay. So let's call this V1, let's call this V2. Okay. And W is spanned by 0, 0, 4, 5. So let's call this vector W. So note V dot, so V1 dot W is equal to 0. Why? Because if I take the dot product, this 1 multiplied by 0 is 0. 1 multiplied by 0, sorry, V2, 1 multiplied by 0 is 0. All these are 0, so multiplied by 0 is 0. So V2 dot with W. So 1 multiplied by 0 is 0. 1 multiplied by 0 is 0. These are zeros, so again these are zeros, so this is also 0. So V1, so or this implies V is orthogonal to W. Okay, so we want to find a third space. So a third space through L, sorry, a third space L through some Z, which is A, B, C, D for same dimension. Find a third space. So find a third space L through Z, which is orthogonal to V and W. So how do we do that? So we say V1 dot Z, this is a vector, V1 dot Z is equal to, so if it's orthogonal, so this is equal to ABC with this one, so I'll get simply A. V dot Z will going to give me A plus B. This should be equal to 0 because V is orthogonal to L. V is orthogonal to L. This is equal to 0, which implies B is equal to 0 because V is orthogonal to L. And finally, if I compute W dot Z, this is equal to, when I compute W dot Z, so W dot Z, AB is no contribution. So we have 4C plus 5D. 4C plus 5D equals 0. This implies C is equal to minus 5 and D is equal to minus, so C is equal to minus 5 and D is equal to plus 4, or C is equal to plus 5 and D is equal to minus 4, doesn't make a difference. So this implies because W is orthogonal to L, So this implies Z equals 0, 0. A and B are zeros, and C is -5 and B is 4. So if I see 1 and 1 here, 0 and 0 here, others are 0, so obviously the dot product is 0. 1 here, which is 0 here, others are 0, so dot product is 0. This is 4 into -5 is -20, -20 plus 20, again the dot product is 0. So this is how you find a vector in the space which is orthogonal to the other space that you are already given. Okay, so let's stop here. We'll start with the fundamental theorem of orthogonality. We'll look at the two different spaces, and then if we have time in lecture 2, maybe we'll start the discussion. What happens if the vector B is not in the column space? If vector B is not in the column space, can we still have a solution? So that is the question that we asked in the first lecture. When is Ax equal to B solvable? So we'll answer that question. And just to give you a heads up, we can still solve Ax is equal to B if we can still solve Ax equal to B even if B is not in the column space. So if you have any questions, you can either email me or we can have more discussions on Mondays and Wednesdays. Until then, thank you.